Okay, good morning on the 8th of November 2012, Biology of Fishes again. Don't have a whole lot of more sessions to go, only about 3 or 4, I think, segments of material that I don't always cover a segment per meeting, so we'll just see how it goes. This was the segment I was talking about last time we met, behavioral regulation of environment. And I'm going to just flip through to the point where we stopped, contrasting behavioral regulation with physiological and pointing out that the two really complement each other and are part of the same, obviously the same adaptive system. I like focusing on behavioral responses of animals because they're so intriguing and actually so problematic in many ways when it comes to methodology. You at one level you've got physics, and physics is pretty predictable. It may take you some really fine equipment and sophisticated methods to determine the rules, but once you got them, it's pretty straightforward. And I think I think of it this way: as sort of a progression between physics and chemistry, and then physiology, which uses both those components and involves lots more noise in a statistical sense, stochasticity. And then you go from the level of physiology to behavior, and you're at a whole other level of noise, much greater. And I think you saw that reflected in the movements of ecofish in the gradient tanks, particularly in the vertical gradient. So much stochasticity that it's, you have to run a whole bunch of repeated simulations in order to be sure of the pattern that you're seeing. So I talked about shuttle boxes, and I talked about the relationship between the value of temperature that tends to be regulated in a gradient where all temperatures are pretty much equally available and ordered from increasing to decreasing as a function of the past thermal history of the organism. And I guess the point I would like to have you be sure to store away is the fact that I think that animals tend to prefer environments that are in some sense optimal. It wouldn't be very adaptive not to do that. So I'm presuming that different kinds of fish have found different ways to optimize their physiology as a function of their thermal status. I pointed out that this, I think it's type 3 of Zahn's classification, tends to be the one that's most frequently encountered. So it talked about predictive regulation of environment being dependent, of course, on the predictability of environment. And that comes in two different stages, really. There's short-term predictability that would be relevant to the individual organism, so that you can imagine an individual moving around in its habitat and learning the lay of the land. We call that latent learning. The way those frill-fin gobies learned the positions of the various tide pools that they were able then to jump from one to the other in. So that's presumably the way you and I learn. We go to a strange town. You come to college. At first you don't know where you are relative to where you need to go, and you get out, your maps, and you learn the paths. And after a while, you can dispose of the maps. What, though, I find as I get older that my map sense has deteriorated. I get confused about whether I needed to turn left or turn right to get to wherever I want to go. In other words, I know where I want to go, and I know generally where it is, but I get a little lost on the path. So I'm not sure what that portends for the future. Probably nothing good. But I think fish have a pretty good sense of prediction for the components of habitat and environment that are stable through time. And in the case of things that are stable over very long periods of time, then those responses can be ingrained or entrained as instincts. But even things that are constant over shorter periods can be learned by individual animals. It's not very useful for their great-great-grandchildren, but it may be very useful for them. Reactive mechanisms are a whole other subset. That's a set of adaptive responses that optimize distribution or have the potential to optimize distribution, or at least keep the animal out of lethal trouble. That depends on the conditions at the moment and where the animal is, and maybe over the recent past, but not on predicting the future. Reactive mechanisms, most folks would separate into two subsets, taxis and kineses, and some people would come along with a third or even a fourth subset, but I think these are the two main ones. Taxis are directed movements by the organism either toward or away from the direction of the source of the stimulus. And the best example of taxic responses are responses that relate to light and light intensity. You know, the animal can look around, you can look around, you and I can look around, we can see the direction where the light is bright. You know, we can see the sun, I guess, or see where the sunlight's coming from. We can look up, see that visual window. And if we got more light than we need, we can go downward and count on the attenuation of light with depth to reduce the intensity, you know, if it's too bright. On the other hand, if we need more light to be able to see, we can move upwards and be guaranteed pretty much that we're going to get brighter light. So these are taxic responses. They're almost akin to predictive responses in a way. You can see that. But they depend on the animal's perceptions here and now. And it's easy to write rules for things like taxis. You know, if I'm too hot, you know, then, well, that probably wouldn't be a good example. If the light level is too high, then turn around and move away from the source, whatever the source is. And you don't need to predict anything. You just move opposite the perceived direction of the source of the stimulus. If, on the other hand, it's too low, then turn around and move toward the source. So these taxic responses work for what are called propagating factors, that, like light and sound. You know, move toward the source of the sound, move away from the sound. If you and this is called these are tropotaxis, moving as if almost if you're pulled or drawn to the source or repelled from it. And it's possible that taxis can work in very strong intensity gradients. An intensity gradient is a gradient of something like temperature or a chemical substance in the water. And the gradient almost has to be so strong that it can be differentiated from one end of the animal to the other. In other words, if the temperature gradient is so steep that you can tell the difference between your head end and your tail end, then obviously you could orient your body and keep turning until you found the maximum signal. If you want to be warmer, move until your head end is the warmest and your tail end is coldest, and then go in that direction until you lose that signal, and then do it again. Or avoid it in the same way. Those are called clinotaxis. Clinotaxis, tropotaxis, these taxis in general don't work too well around corners because you got to have a straight line shot to your source. Kineses, on the other hand, I think are probably a lot more applicable in most situations. A kinesis is defined as an undirected movement, a movement in no particular direction, but it's in response to the variation in some stimulus. So what's the distinction? Taxis are directed movements, toward or away from the apparent source of the stimulus. kineses are undirected movements that depend on the intensity of the stimulus, but are random in their direction. And so again, kineses, we're going to kind of focus down on and talk about subsets of kineses. So we got, what do we got? We got environmental regulation, two broad subsets of ideas, predictive and reactive. And then within reactive, we got taxis and kineses. And now within kineses, we've got orthokinesis. And orthokinesis is the idea that, and let me go to full screen view so you can see it a little better here. An orthokinesis is defined as a response in which the direction of motion is random, undirected motion, but the speed or the frequency of movement tends to vary as a function of the intensity of the stimulus. For continuously moving animals, it's the speed of movement. For discontinuously moving, it's the frequency with which they make a movement. And the way it has to work in order to achieve any kind of hope of environmental regulatory response is for the speed or the frequency of movement to reach its minimum at the preferred level or the optimum level of the environmental factor. Why is that? Logic says, or logically it must be, if you think about an animal moving around randomly, going in random directions, the faster it moves or the more frequently it moves, the faster its rate of diffusion away from the point where it is to some different place. In the limit, if you stop moving, you stay forever right where you are. And so if that's optimum, that's great. And one of the most dramatic demonstrations of the fundamental ideas of orthokinesis involved a series of experiments done years ago by folks using cockroaches. And they had paper cups with a little hole in them. And they had them at thermal gradient. And the cockroaches got into the cup that had the right temperature and just stayed there. So they all accumulated in that cup after a while. So that's a good example of orthokinesis. Speed or frequency of movement least at the optimum. I say there it's not a very effective concentrating mechanism. And I'm going to demonstrate that to you by playing with a little model that I built and published on orthokinesis. We'll see if I'm right or wrong about that. So, clinokinesis, ortho having to do with speed or frequency of movement, clino having to do with the rate of turning, or the angle of a turn, if the rate is constant. And here it has to be just the opposite in order to achieve any kind of hope of aggregation or concentration or selection. You have to have a maximum rate of turning where things are best, and a lesser rate of turning as you go away from the optimum situation. Why would that work? Well, as you're moving along in long straight lines, that tends to take you further and further afield. So that's analogous to diffusing at a very fast rate. But if the turning rate is high, then you're basically just spinning in a circle right in one place, regardless of how fast you're moving instantaneously. And so you tend to stay where you are. So if, when conditions are good, you find yourself in a good situation, you just turn very frequently, you tend to stay there where things are good. And then if things deviate from being good, then the path length gets longer and longer. You turn less and less frequently, or you turn at a slower rate continuously. And then you tend to move away from that place. And maybe if you're lucky, you find a better place. So this works even in the absence of a gradient. As long you could have a patchwork of environment, and this kind of thing could work similarly orthokinesis. So, each of these two, I say, has a problem. Before I leave these, I'm going to just give you a little preview of the problem that I'm going to demonstrate with simulation, and that is that it only works really well in physically bounded systems. And where this really was first developed and demonstrated in a convincing way for fish was work done by V.S. Ivlev, the same guy that did, I guess, the same guy that did feeding electivities. Ivlev took fish and put them in gradient tanks and showed that the distribution could be represented as sort of the inverse of the speed of movement. It was an orthokinetic approach. But in the case of Ivlev's experiments, the lethal environment didn't exist. In other words, there was a physical endpoint on the gradient at a sublethally low temperature and a sublethally high temperature. And so those ends represented completely reflecting barriers so that the animal could never make really too bad a mistake. It was always reflected back into the middle of the distribution. And so in that situation, yeah, wherever you move slowest is where you're going to aggregate. But think about it this way. If you die, you don't move at all, so you're really going to move slow there. And so what you end up with, if you simulate this in an unbounded system, is two piles of dead fish, one at both lethal levels of environment, because there's nothing to turn the animal back. It just keeps moving, and it, in this case, for example, the turning rate goes down and down and down. So by chance you make a mistake, you get out into too high or too low, and you swim even straighter paths, and which takes you even further out into too high or too low, and pretty soon you're out in lethal country. You swim off to oblivion, either in straight lines according to clinokinesis, or increasing your speed of movement to the speed of light. Well, not to that much, but so in this case you're just swimming off at a high speed into an extreme world. So what is there an alternative? And in the paper I'm kind of thinking about in the back of my mind on something like behavioral mechanisms of thermoregulation in fishes, which I think was published in American Zoologist, suggested an alternative that's sort of some of both, and it's called clinokinetic avoidance, and it's this mechanism that's invested in ecofish. Clinokinetic avoidance behavior comes down to a really easy to state simple rule. And that simple rule is move, and if things get worse, increase the probability of going back the way you were moving, going back where you came from. If things seem to be getting better, then don't do that. Just keep on keeping on. So that's the rule. Increase the probability of rate of turning whenever your recent experience implies a worsening environment. Some other folks have called this self-steering behavior, and the other day I was alluding wrongly to another paper and criticism we got after the fact. I got the criticism on this paper, this idea. Some guy writes me and says, hey, we've known this for years about bacteria and the way they tumble. They tend to tumble more when they find themselves in situations where things are getting worse, and so they don't go any further the way they're going, and then when things are getting better, they tumble less. So that's in a way that's turning rate. I didn't know about that work when we did that paper. So, it works out to kind of a contingency table. Maybe it's easier to see it that way. It requires an additional piece of information here. You got to not only know about the value of present environment relative to all possible environments, you got to know about the change from the present to the recent past. You got to know about the change in environment in order to know whether it's worsening or improving. It could be bad, but if it's improving and bad, you don't want to change your direction. You want to keep on doing it. It's working. If it's good, and you detect that things are getting worse, then maybe you don't care. It's good enough, but maybe if you're going to do anything, you might want to increase the rate of turning if things are good and you detect that they're worsening. And so here's the way I sort of laid it out. Over here's level, too high, too low. Think about temperature. Too hot up here and too cold down here. And here's just right. It's like Goldilocks, And so there's the value of environment, the present environment, relative to some ideal. And on this axis is the way the value is changing over time, over the last step, or over the last few steps. If it's getting lower, getting colder, let's say, but it's too hot, then that's good. And you want to turn less. You want to keep on doing that. It's working. But if it's getting too hot, if it's getting hotter and it's already too hot, the last thing you want to do is keep on going in that direction. Out of the frying pan into the fire. So in these two quadrants, things are worsening. And you should turn more as you go out there. And maybe you should turn progressively more as you go further away from this intersection between no change on this axis, that's stable, and perfect conditions on this axis. If there's no change and you're in a perfect world, you don't have to do a thing. You just blunder along and just be happy, fat, dumb, and happy. On the other hand, if things are, if you're further away from the perfect condition, out in these quadrants, further toward the corners, then maybe you want to increase your rate of response in the appropriate direction. So that's what Ecofish does. Except, what is it using? Ecofish is using metabolic scope for growth, and there's no way to have too much of that under the model. And so this table gets folded on itself. It's only the, it's kind of like it's not good but better. It's only half of that vertical here. Can never be too high. It's just too low. So this axis just starts down here at 0 and goes up. So I like to argue that behavioral enviroregulation using this clinokinetic avoidance idea, in other words, when it's metabolic scope that's being regulated, that's being responded to, then this amounts to a super mechanism for optimization of environment because it integrates all of the components of environment. And it does it in the context of the history of the animal. So I call it a speculative super mechanism. It would permit truly integrated behavioral enviroregulation fully accommodated for environmental history and for changing activity demands of the system. It would permit appropriate responses to vague directive factors like structure of the habitat or the presence of bugbear. I use that as an example to illustrate it. But, there's a problem. There's always a problem. And the big problem, of course, is that what's going on, or is it something totally different that I never or anybody else ever dreamed of? And that's always a possibility, But, I guess this is a point of philosophy that I'd like to have you sort of think about, particularly if you have a future in research. And that is, using models to sort of narrow your focus and keep you from wasting a lot of time on things that are patently impossible. If you know something about statistics, you don't prove hypotheses. You just reject the ones that are more false, probably, and you fail to reject the ones that are a little less false because you don't have enough data and there's too much random stuff going on. But simulation modeling, the way Ecofish reflects it, represents an effort to organize what you are thinking in a way to explore the various pathways to the truth, in a very complex. All of this sort of thing is obviously really complex and way wrong, but at least you're making some progress, you feel, if got a model that can accommodate a situation that you never even dreamed of when you built the model, and yet it can do something that's reasonable in response. And every year I have students who suggest projects in biology of fishes among the graduate students that I didn't think about. And it's always heartening for me to see a model, an application in a new direction, result in stuff that's understandable. And even if it isn't, sometimes the outcomes of modeling cause you to say, okay, that's different from reality. The model is saying something very different from what really happened. So why? What could be making that difference? Okay, well, we can't do much about the reality. But we can go into that model and say, well, if this were working this way instead of the way I thought it was working, then that would be consistent with reality. But now, is it still consistent with the old reality, all the other experiments? It has to do both. It has to, and a good model can accommodate a whole broad set of possibilities and not fall flat on its face. A bad model will usually fail the first time you try it on something new. It just didn't work. So, I don't say that the ecofish and its predecessor, ecophys.fish, is the truth, but I do say that it's useful in terms of helping find a path closer to the truth. One of the big flaws that I see in this idea of maximization of metabolic scope is what's the proximal signal? Thyroxine, Duncan McKenzie would say. No, he wouldn't say that, but maybe it is an endocrine response. Maybe fish feel good. It's feeling good. And if you feel good, then keep doing it. Actually, there was a fellow named Jens Balchen, a Norwegian, some years back, who had this idea that it's a comfort factor. That fish manage their activities and their behavior like people to achieve a comfort factor. And maybe that's what this is, Increased metabolic scope for growth is analogous to a comfort factor. What you want to do is increase it. And how does it get sensed? I don't know. I used to think maybe it was partial pressure of oxygen in venous blood coming back, but looks like that's pretty much independent of everything now. Maybe it's the production of some endocrine product. Maybe it's some analog of heat shock proteins, but comfort proteins. But it has to be short term. It has to be quick in order for it to be effective in a gradient type experiment like we simulated. It can't be over days. It has to be over seconds. And that's going to be a requirement that makes it a little tough, So I guess you see the point, and the point is that I don't know the truth, I just know that it's interesting to think about it. So, I don't know whether we made any progress in that bit of monologue or not. So you know how it works. You know enough about ecofish now to know that ecofish is working to maximize metabolic scope for growth under the existing model, and that means it wants to keep itself away from these limiting levels of low DO. And it's going to be tending to continue moving in the direction it's moving if, in fact, this difference between the blue line here called routine and the red line called active gets greater. And once it gets to maximum extent, it doesn't care. It's going to be pretty much moving randomly at that point. That's kind of like being in the middle of that contingency table. That's in terms of oxygen. There's the way it would look in terms of temperature under the model that's in ecofish. Metabolic scope for growth will be maximized at the optimum temperature and be pinched off progressively as you go towards lower and upper extremes. If routine rate is caused to be greater or less at one temperature than another by, for example, the presence of bugbear, then that changes everything. That changes where it's good and where it's bad in the system. Relatively good and relatively bad. So, here's some little models that I'm going to put up on the server for you to look at, and they represent these different things that I've talked about. The first three of these, ortho, clino, and Ka avoid, are all temperature regulation, thermal regulation models, and they are classic in the sense that all they do is tell you, all they say is that ecofish is sensitive to temperature and temperature change in the case of the Ka avoidance, and responds to that and regulates it. And then the final one here is to show you this leap from a single factor temperature to metabolic scope. So it's metabolic scope for growth, clinokinetic avoidance. It's using clinokinetic avoidance to maximize metabolic scope for growth rather than just to optimize temperature. So let me pause and open these. I'm going to go through these one at a time and run them and show you the consequences. Okay, we're back, and I've got Orthokinesis open. This is the version that you can download from the archive as soon as I move it up there and post it. As I was opening this and trying to decide the version of Stella to use, I ended up using Stella 6, which is the version that I like to work in. I was thinking about the fact that IC Systems has now released a new version of Stella that's been promised for a couple of years. It's Stella 10. And I was also thinking about the fact that I downloaded my copy and tried to open Ecofish and it wouldn't. So for the first time, Ecofish built in Stella 6 won't open in the latest version. And I think it's got to do with some labeling conventions. If you read the README notes that are released with the new model, it talks about some things that are changed conventions. I'm not sure why the changes, like naming of sectors and things like that. Can't use an ampersand in them anymore. And I guess it's one of those things. I presume that I could go in and invest a few hours or days and probably take all of the Ecofish variants and convert them to forms that would open. But you know what? I'm probably not going to do that. So, I'm kind of glad to still be doing this when Stella 9 is still available to you students. I was just thinking how it would have been had Stella 10 come along a year ago, and this fall I had gotten ready to offer you copies of Stella 10, and it wouldn't work for you to run Stella or Ecofish. Fortunately, 9 works, 8 works, 7 works, 6 works. So I don't know, maybe that's just a minor glitch, and maybe the first revision will make it compatible, backwards compatible. Well, you can program just fine in Stella 10. I did that. It looks about like Stella 9, actually. It's got that same tab look about it to the side instead of like this. But it won't open Ecofish. All right, so this is my little orthokinesis model. And it's as simple as I can make it. And the purpose of that is to just let you focus on what's going on instead of all of the bells and whistles. And what we have here is Ecofish moving back and forth in a spatial one-dimensional gradient. S is the position in that gradient. And the gradient extends from minus 100 fish lengths below zero to plus 100 lengths above zero. And I think out of the box it's zero. So Ecofish is released at the midpoint in this long tube that's 200 fish lengths long, 100 on each side, each direction. And there's a relationship between the temperature of the water in that tube and the position. And the relationship is set up with just just a simple linear equation. Well, that's not the linear equation I'm looking for. That's the one that decides whether he dies or not. Let me pause and look at yeah, okay, that was the right equation. What I wanted to focus on was just this middle part here, which says that the temperature where Ecofish, or where this virtual fish is the intercept plus a slope of the gradient times the position. And the way TA naught and G are set is designed to achieve extremes of, I think it's 15 and 45 degrees at the extreme ends of the gradient. And under the rules of this model, ecofish dies instantly whenever it exceeds 45 or falls below 15. It starts at 25, and so that's, or maybe it's, 35, I guess. Yeah, if the ambient's less than 15 and the fish isn't already dead, or the ambient's greater than 35 and the fish isn't already dead, then set the death temperature to ambient temperature, else don't do anything to it because we want to leave it 0 until the ecofish dies. So it's 15 and 35. It's 10 degrees up, 10 degrees down. And so what we're saying is that in this particular version, the probability of a turn is always 0.5 for each step that the virtual fish makes. And so the direction is random, but the speed is going to be influenced by the temperature. And it's going to be the minimum of two things, either a bias term or 3. So it's never going to go above 3 body lengths per second is the way this is written. And bias is a quadratic function of temperature. So bias is going to reach minimum when the temperature is at 25, and then it's going to rise as you go away from 25. And wherever it intersects a constant that's 3, it's going to stop. And we can see this graphically. And maybe it'd be easier, instead of poking around in here and explaining all the nuances of Stella, to just run the model and let you look at the results. And this particular graph is showing ambient temperature of the virtual subject over 100 steps, and that's all we're doing here. And the temperature range is 15 to 35. That's all that's possible. You go below 15, you're instantly dead. You go above 35, you're instantly dead. You pay the price for a mistake. Ecofish, pays the price too, but it's a more gradual way in that there's an accumulated lethal dose. Remember the lethal factor experiment, so you don't die instantly if you're extreme. So I'm going to start running this, and there's a good run, right? Sort of looks like ecofish. We start out at 25. Sure enough, orthokinesis worked. The virtual subject stayed within bounds, ended the race at 24.1, lived all 600 seconds. This is a 6-second time steps, 100 steps. And this is all consistent with the paper that I was talking about, published in American Zoologist. So that's the reason for the 6 seconds, because I'm actually mimicking the Idlev experiments on little salmon and little carp that he did in simulation. That's the reason some of these are kind of artifactual to that context. So let's try that again, huh? Worked out great. I'm going to get the little running guy up here. One of the things I like about the old versions of Stella. So I can just click the run button and we can see it run. Oops. So that was 1 out of 3. Didn't end up too well. What happened was, you can see the progress here. Remember, this is orthokinesis. The further you get away from the optimum, which is 25, the faster you go. And once you get away, then you tend to go even faster further away. And if you don't change your direction and go back. So you can see that the spacing between the points gets greater. This is now 1 time step in here. You can see how large that interval is compared to down here, for example. Actually, that's probably 2 time steps. That's probably 1 right there. You can't see, I don't mark each time step. I'm marking every, if you continue going in the same direction and you're moving along 1 step, basically the way it looks on the graph, even though but you can see right here that that's sort of an indication of how big the time step is in there, how far you would move in 1 time step. And here's how far you would move in a time step if you're at this temperature. That's why. So in this case, the virtual subject lasted only 216 seconds. and died at 36.6 because it jumped all the way from 35 to the lethal in one step. Instead of, at 35, it went to 36.6. Let's try that again. So 1 out of 3, 2 out of 4 failures, Chris. That's not good. 50%, you wouldn't do too well if you only had a 50% chance of surviving the experience here. And there's, 3 out of 5, and now 3 out of 6. And there's only 3 failures out of 7, so we're doing okay. 3 out of 8, so maybe, 4 out of 9, and 4 out of 10. About a 40% failure rate, I think. Now, I've had students run these things, 100 times and see how many failures they got, and I can't recall what it is, but it's probably in the 40% range. So that's the way orthokinesis works. In a world where the system is not bounded. In other words, it's bounded really in this case because you could anytime you touch the ends of the tank, you're dead. So you pile up there, right? So in this case, the direction of movement is random. There's always a 0.5 probability of changing direction at the end of any step. But the length of the step is increasingly long as you go away from 25 because the speed within that step is faster. So that's orthokinesis. And we can look at some of these other graphs and there's the gradient, and this shows you the simulations, and it's a comparative graph, meaning that the data are added on top of each other, superimposed, so you don't get rid of the old when you run a new one. And you can see that all of the tracks are along this 15 degrees at minus 100, 25 at 0 position, and 35 at the 100 position. So it's a linear gradient, just like the one that we had Ecofish operating in. Graph 3 shows the probability of a turn versus the ambient temperature, and you can see that it's flat. It's 0.5 at every step. And then graph 4 is the one that shows you the speed as a function of temperature. And there's where you can see the parabolic U-shaped function that looks very much like the one I showed you in my rough drawing in the presentation I did. And the only thing I added here was I didn't let the speed of Ecofish go to infinity, as parabolic things are likely to do. I let it be constrained to something reasonable, a maximum of 3 body lengths per second. So the speed at the optimum temperature is 1 body length per second. And that increases parabolically to 3 body lengths a second at whatever temperature it worked out that this parabola intersected 3. All right, so how about, and you're welcome to get this out and play with it yourself and run a whole series of trials if you'd like to just see how this works. How about clinokinesis? How does that work? Okay, it looks just the same, or it will as soon as it opens. I mean, the schematic, the drawing, the model diagram looks exactly the same. The differences are, notice that bias is now affecting the probability of a turn instead of affecting the speed. Before there was a connection from bias down to BLS, and now there's a connection between bias and the probability of a turn, and BLS is set constant at 1.5 body lengths a second. So you can probably anticipate how this is going to perform. Well, maybe you can't, So with the probability of a turn increasing as you go away from the optimum, here's a case where the probability of a turn was so low that the Ecofish made it. Well, that's not right. The probability of a turn is is it, you know, I get it. Okay, my mind is focusing on this. Let's look at graph 3 here a little bit. Maybe that'll help me see what the probability of return is doing. I'm going to run a few runs, and you can see that Ecofish is building its repertoire. I mean, there are multiple runs, and the different individuals are doing different things, but in general, there's a tendency for the probability of return to reach a maximum at the optimum, which is just as clinokinesis says it should, and then to fall away as the temperature goes more or less extreme. It just happens that this yellow color you can't really see over here, but you can see let me see if I can get it change color by running a few more. I mean, there's a whole series of yellow points there. Can you see those at all? Yeah, you can see them. So here what happens is the probability of return is maximum at the optimum and then decreases as you go away from the optimum by the same parabolic function that I used for speed before, except in the other direction. And also notice that I have truncated this at, I don't let the virtual subject ever be perfect in its behavior. It always has a probability of failure. So if you'll notice, the maximum value of the probability here is 0.95. So there's never more than a 95% chance of doing the right thing. And there's never less than a 0.05% chance of doing the wrong thing. So I constrain it to go between 0.05 and 0.95. The gradient is exactly the same as before. Obviously, we'd want to use the same experimental arena. And let's see what graph 4 is. Graph 4 shows you the swimming speed, which is now fixed at a constant value. So now it's probability of return that changes instead of speed. But and you get a different look, you know. These high probabilities of turns at the optimum means that the Ecofish is just spinning in a circle there. But periodically, what you find is the same kind of failure that we saw with orthokinesis. You know, what's happening here is by chance, Ecofish wanders away, diffuses away from that optimum place and gets off into less optimum country, which makes it even more likely to continue in that direction because it's making lesser turns. And you can see that these steps are getting longer and longer as we go to oblivion here. So let me just, there's another failure. Get my running guy up here so I can do a bunch of these for you. And I think that when we have tested this, we have found that, and by the way, the probability of a failure up and down should be the same. The fact that they're not, I'm not sure what that says, just I guess the chance of the luck of the draw. It does seem like there's a bias for failing on the downside, though, and I don't know why that should be, because you can see the symmetry. There's no Arrhenius effect built into this Ecofish, or this virtual subject. But I think in cases where we've done a large number of runs and kept track carefully, we found that the failure rate is about the same between orthokinesis and clinokinesis, given the same kind of limits. So, what about clinokinetic avoidance? Again, the model is going to look the same. But now, we've got a more complicated arrangement involving you have to compare the present value of temperature with the previous value, decide whether that's getting closer or further away from the preferred. And if it's getting further away from 25, then increase your probability of return. If it's getting closer, then decrease. So if you're going towards 25, from either direction, you have a lower probability of turning. But if you're going away, you have a greater probability of turning. And you'll see the way that gets resolved on this graph of probability of turn here. So let's run a few trials with this before we bother with that. And notice the look of this is more like orthokinesis, really. I don't know how many times I've hit that run button, but I don't think we've had a failure yet. So I hope you're getting the impression that, maybe you're flopping around a little bit more. Maybe you're using more of the thermal spectrum that's in the zone of tolerance, but you're not killing yourself very often. In fact, we haven't had a single failure yet. I don't know how many times I've hit that run button. I think the failure rate is less than 1%. I think it's about 40 or 50% for orthokinesis and clinokinesis under these conditions, but only about 1%. Periodically, you'll have somebody, that just does the wrong thing consistently, as if it's trying to do the wrong thing, and falls off the edge of the earth here into lethal country. But for the most part, it just doesn't fail in that direction. It is more, it flops around within the space more, if it, than say clinokinesis does. But clinokinesis is either real good or real bad. It either stays in the middle or it dies. So, how about same linear gradient of temperature as before? So we're operating in the same world here by the same rules. You're dead if you fall below 15 instantly or above 35. But here's a sort of horns of a dilemma type deal. Here's the probability of a turn versus TA here. And the up and the down facing and the up facing things reflect traveling in different directions. So if you're going up the gradient, the probability of a turn is up the gradient would be improving. Probability of a turn is low. As you get to 25, you don't care. Probability of turn is 0.5. But if you go above 25 and you keep going, the probability of turning back gets higher and higher and higher. When you make the turn, you jump from this curve down to this one. And now the probability of making a turn, now that you're finally going in the right direction, down the gradient towards 25 is low until you reach 25. Once you pass through 25, if you still haven't turned, the probability of a turn continues to increase. So this, let's see if I can alt. I think this would work, yeah. So, what I'm going to do here is draw the two. Okay, that's swimming. That's the situation if you're going in that direction. Regardless of where you are, that's the situation if you're going up the gradient. And then color blue. Here's the situation if you're going down the gradient. And when you turn, you jump instantly from one curve to the other, because then you're going the other direction. So you jump instantly if you happen to turn right there, and most times you do, because as the probability of turn gets higher and higher, chances you don't turn get lower and lower and lower with each progressive step in the wrong direction. So then you zip over here, and now you're down here on this curve with a low probability of turn in the next step. So that's the way that works. So finally, let me show you metabolic scope for growth. Let's see, have we looked at all the stuff here? Yeah, well, all this says is that swimming speed is constant under this clinokinetic avoidance model. In other words, I've used turning as the response in clinokinetic avoidance, as indicated by the clino part, instead of orthokinetic avoidance, which I guess would be speed. You could do either one, I think, but I've just elected to keep speed constant. You could let speed vary with temperature and let the probability of a turn be the thing that's a response. And that's what ecofish does. The ecofish actually swims faster or slower, as well as having a greater or lesser probability of a turn depending on the thermal regime, because of the Arrhenius effect. This little model doesn't have an Arrhenius effect. So let's take a look at clinokinetic avoidance, where metabolic scope for growth is the response to which turns are being made or not made. And as I said, I'll put all 4 of these up. Okay, a little more complicated because you got to get into the metabolism part of the stuff. And so now what's happening is the temperature is having its effect on metabolism, both active and standard metabolic rates. There's a Weinberg factor that is the number of times that routine rate is multiple of standard, and 2 is sort of the nominal value. But notice this was also equipped to have a bugbear component here. If the absolute position of the virtual subject in the spatial gradient, position S, relative to bugbear is less than 20 units, then triple, go up by another, go from 2 to 3 on Weinberg. In other words, triple standard metabolism to get the routine instead of just doubling it. So that's just so you can play with bugbear in the context of this simpler model. All of these things come together, and these are mirror the components that are also in EcoFish to affect the metabolic scope for growth. And this lagged metabolic scope for growth allows you to keep track of metabolic scope for growth now versus metabolic scope in the last step. Same way that I didn't mention this, lag direct allows you to remember which direction you were going in the last step, so you know whether a change occurs or not. And so now it's metabolic scope for growth and the change in metabolic scope for growth that are affecting bias instead of temperature per se. Temperature has no input on the behavior here except through metabolism. And that's what Fry said. That was his central tenet in his whole argument about the physiological classification of environment, is that the effects of environment on animal activity are through their metabolism. And this is faithful to that principle, that the effects of environment, in this case temperature, are through metabolism on the responses of the organism. So again, EcoFish pays the ultimate price if it makes a mistake. If it goes off either above 35 or below 15, it dies. Let's open some graphs here, and I'm not sure why I've got these positioned here. I guess I had to move them out of the way from up here. Here's again the same graph you've been seeing, TA versus position, or versus time, a step, number of steps. 100 steps represent 600 seconds, as it turned out, 6-second steps. So run that model. I'm going to do better than that. I'm going to get my little guy up so I can do a lot of them easily. Okay, so what you see here is going to be behavior that looks a whole lot like clinokinetic avoidance, where it's just temperature that is modulating the response. But I think maybe there's one little difference here, and Chris has already seen it, and it is the fact that the position of this virtual subject along the temperature axis is shifted up, so 25 is no longer the optimum. And in fact, it isn't. The optimum temperature for this virtual fish is that temperature that maximizes metabolic scope for growth. And that depends on what the effects of temperature are on active metabolic rate, standard metabolic rate. And it turns out that temperature is probably about here, somewhere around 27. I don't know what it is. It's not written in. Notice, we didn't say, hey, EcoFish, go select 27. We said, maximize your metabolic scope for growth. And oh, by the way, it turns out that's 27. It's not a direct effect of temperature. Yes?
And that's under oxygen-saturated water, right?
This says that there is no effect of oxygen. Valdemar asks, is this oxygen saturated? So yes, it would be where we're assuming there is no limitation of oxygen. Now, in the real EcoFish model, in the EcoFish version of this, of course, everything that's in the model that would affect metabolism would have some effect on the process, the response. And sure, and if you look at the presentation that I did that is designed to extend Lab 5, where I talk about ecofish regulating environment in two-dimensional space, that's the main purpose of that presentation. Before I get into that, I actually go off on a tangent and talk about what happens if oxygen is insufficient in the thermal gradient and demonstrate that sure enough, if you reduce oxygen concentration in the thermal gradient, you're going to reduce the preferred temperature of ecofish. So it's actually there, and anybody that wants to repeat that and explore it in finer detail as part of the project that you might do is welcome to do that. Okay, so I think the point of this is ecofish manages, even though it's getting close up there, it's asymmetric now. It's got a higher probability of dying at the high temperature than the low. It's still not dying, it's still managing to keep on keeping on, despite the fact that it's up here hugging the upper boundary. So I don't know how many times I've hit the run button now, but lots. You're welcome to hit it as many times as you'd like. Let's play with bugbear just to bring that. Let me see. Before I do that, let me look at these other graphs and see what's in them. Okay, there's the last graph we did. Here's the graph of temperature and the gradient, same as before. 15 to 35 as the S goes from minus 100 to plus 100, so that's all the same. Now we've got kind of an asymmetric looking probability of a turn versus ambient temperature, and that has to do with the asymmetry of metabolic scope as a function of temperature. And here we've got, here I'm just saying that this virtual fish, like the clinokinetic avoidance fish, like the clinokinesis fish, swam at a constant speed, 1.5 body lengths per second. And I don't know what graph 6 is. Graph 6 is metabolic scope versus temperature, just to see that it is asymmetric. We maximize metabolic scope given the parameters that are out here. Here, we maximize metabolic scope right there. What's that, about 29 degrees, which is about where ecofish maximizes it for all conditions being optimum, everything else. So, one other thing, bugbear. I got bugbear set in there at 150 time steps, which is 50 more than we're going to do, or been doing, so bugbear never came out. What if we put bugbear into the picture at, say, 25 time steps? We know where it's going to be. It's going to be, or do we know that? I guess that's what bugbear is it? Better be sure if the absolute value of S minus bugbear is less than 20, then 3 else 2. Oh, no, I take it back. I think we had bugbear positioned in the gradient at 150 fish lengths away from 0, which meant that it was out of the gradient. And so what I need to do is put bugbear into the gradient, and I don't want to put it in at necessarily at 25. Where I want to put it is right where metabolic scope for growth would otherwise be maximum, right, in order to see the contrast. And where would that be? Well, go down here and look at this graph again. It looks like it's going to be at about, I need somebody to help me with the math. Let's say it's 29. What's the position of S? Well, I don't guess I need help with the math after all. I just need to go and look at the graph that is temperature versus S and ask the question, at what value of S is the temperature 29? It looks like it's about, what would you say, about 80, maybe? 80 lengths, 80 positions. In other words, I'm just looking over here and saying there's about 20, that's 25, that's 30, this must be about 28. 28 must be about 80. Oh, you're right. This is 50, so it's like 40. 40, thank you. So I would have screwed up again. I would have had bugbear coming out at a place in the gradient where the metabolic scope for growth was already 0, which wouldn't matter then. So I'm going to put this in at 40. Good thing I had some help from my friends here. We'd have been in trouble on that one. Now let's see what ecofish does. It's looking more kind of clinokinetic here. Why is that? Because I think right there is where bugbear is, and it's there all along. It doesn't come out at a certain time. It's out from time zero. It just jumps in the gradient instantly, and there's no attenuation, nor the strangeness never goes away in this case. And so what's happening here is that the virtual subject would like to go, back up here, would like, in a teleological sense, to the previously preferred temperature, but now bugbear's sitting there scaring it away. And so it didn't. It's just, whoops, there's a case where it got above it by accident, stayed above it, because every time it tried to go below it, it hit bugbear, and its metabolic scope for growth went down, and so it went back up. So it was caught between a rock and a hard place, between the frying pan and the fire, maybe here. The frying pan being down here, and the fire being up here at 35, I guess. And here it's below. So it's the same kind of behavior you saw with ecofish, where it's flipping above and below, except here it's a little cleaner because there's, things aren't changing through time, really. Here's a case where ecofish marched straight up and was brave. You realize that we're using these human words here to describe behavior that's completely automatic and completely robotic. But that's the tendency, right? We look at animals, real animals, and we use human words like, hey, little ecofish was brave here. It girded its loins and it dashed across, it flaunted itself to bugbear. It said, I don't care, Well, it didn't do that at all. Just the probabilities worked out, random numbers worked out. And in this particular run, ecofish went across the position of bugbear and stayed there.
Where did 40 come in that we looked at earlier?
Which was it? Ray says, where did the 40 come in?
Yeah.
You mean the 40 I put in here for bugbear?
Yes.
It became in here because I said, where do I want bugbear to show its ugly face in the gradient? In the spectrum from minus 100 to plus 100. Or no, in the spectrum from, yes, I guess that's right. In other words, the way we got the 40 was, and I thought you helped me get it. I thought you were the one that corrected me here when I went out to graph 2, and I said, hey, I know that metabolic scope for growth of this particular virtual subject is maximum at about 29 degrees, because that's where it peaks when I looked at the growth metabolic scope. In other words, I went to this graph first, graph 3. Whoops, not graph 3 anymore. See, now I got the bugbear in there, so I can't see that. Well, we can take it out. Well, no. Here's how I got it, Ray. I said 29 is where metabolic scope for growth will be maximum. Go over here, go down to the S-axis, and realize that the point on the point on this line where the y-axis is 29 is x equals 40 or so. It's not 50. I first said 80, and you said, no, it's not. So I thought you were the one that told me how to do it.
Well, I could read the graph. I wasn't understanding why.
Okay, well, why is because we want that value, and I'll just use my old Alt-Z friend again. In other words, we've said, hey, here is approximately the temperature that maximizes metabolic scope. So let's just go over here and hit the graph and then go down, and not going down very straight, that's because my hand is shaky, to this point and ask the question, what is that on X? And it's 40 approximately. It could be 35 or 42, I don't know. I just put 40 in. Nice good round number. That's how we got the 40.
And so then bugbear
jumps out instantly at time 0. It's already there at position 40 in the gradient. And whenever ecofish is within 20 body lengths of that, its Windberg goes from 2 to 3, which reduces its metabolic scope for growth just in that. And I think you can see this kind of notch. Let me Alt-Z back out of that. You can see this notch in graph 3. Maybe you can or maybe you can't. It's superimposed so many times, but, well, I don't see it there now. How do you interpret these things if they're confusing? And the answer is, as I was explaining to Allison before class this morning, for those of you who are working on projects, table it. Table every single step of the model and then see how things change. You know, when this variable changes this way, how does this variable change? So that helps you to, you know, interpret what's going on in Stella. But I'm confident that what's going on is every time the virtual fish gets close to position 40 in the gradient, where the temperature should be just right, suddenly it's influenced by bugbear to cause its metabolic scope to be reduced between the Windberg of 3 and Windberg of 2 goes to 3, and that leaves less room between routine metabolism and maximum or active metabolism, which is what we argue is being maximized. Is that making some sense to y'all that are in the room? That's the reason it's so important to have somebody sitting there in the room asking or looking you in the eye. Otherwise, I don't know if it's making sense or not. But I think you all are getting this. I think you're getting it. I think you're getting the bigger picture, the bigger message too, which is that, hey, it's really useful to be able to put things together in a systematic way, and that's the reason we call it systems modeling, to see the consequences of certain assumptions, certain paths of cause and effect. And I would submit to you that that's the way science has got ahead. It's too expensive to do it the old-fashioned way, where we do these simple dichotomous tests of simple hypotheses and then move on to the next dichotomy. You know, I think it's to the point where we're going to have to say, I think A causes B causes C causes D. Now I'm going to change A and look for D. And if I'm clever enough to build a model of that cause and effect sequence, I should be able to predict D, given A. If I can't, then I got to start over, you know, or somebody else. I'll just hand this, you know, I'll pass on my turn to the next scientist and let that person try. You know, I think it's too expensive to do. You know, I guess I'm being blasphemous here. You know, but I think there's some truth in that. Maybe I'm overstating it as usual. But the idea of just doing it the good old-fashioned way and dichotomous testing, I don't think anybody's got the patience or the money to do that anymore. You have any thoughts about that, anybody? We're out of time here. I wouldn't mind if you disagreed with me. You know, I would say that it was a sign that you're thinking if you did and said, hey, you know, well, that's not going to work because, you know, you're going to lead yourself down the garden path to a real impossibility if you do it that way, instead of going step by step every time, being sure before you make the next step. That's the way that's the way I was taught you had to do it. But somewhere I got a different idea, a more radical idea. Anyhow, so we're going to quit for today. Run out of my time, but I think it's been, from my point of view, from my point of view, this has been a good session that I was able to sort of expose myself and my thinking to you and let you have it to decide for yourself, you know, if it's useful or not. All right, we'll quit. See you next time. Next time we're going to take up activity patterns of fishes in their habitats, so a little bit more back to field kinds of situations.